Every time you hear about a new quantum computing milestone, a new record number of qubits, a new demonstration of quantum advantage, a new billion-dollar investment in the industry, there is a word that appears in the technical literature but almost never makes it into the headlines, a word that quantum physicists think about every single day, that shapes every design decision in every quantum hardware lab on Earth, that has single-handedly prevented quantum computers from being useful for the past 30 years, and that will determine whether the quantum revolution delivers on its extraordinary promises or remains forever just around the corner. That word is decoherence. And if you have read about quantum computing at all, you may have seen it mentioned briefly as a challenge, a hurdle, a technical problem being worked on. What you have almost certainly never seen is a complete, honest explanation of exactly what decoherence is, why it is so catastrophically difficult to defeat, what every major player in the quantum computing industry is doing to fight it right now, how close the field actually is to winning that fight, and what happens to the quantum revolution if they do not. This video is that explanation. By the end of it, you will understand the single most important technical concept in all of quantum computing better than most people who casually follow the field, and you will understand why the developments happening in 2025 and 2026 represent the most credible progress against decoherence in the history of the field, and why that progress still has further to go. Like and subscribe right now, because what I am about to walk you through is the foundation of everything else in quantum technology, and almost nobody covers it at this depth. Start with what a qubit actually is, because you cannot understand decoherence without understanding what it is destroying. A qubit, a quantum bit, is a physical system that can exist in a quantum superposition of two states simultaneously in a superconducting qubit. Those two states are different energy levels of a tiny electrical circuit cooled to near absolute zero. In a trapped I don't qubit, they are different electronic energy levels of an individual atom held in place by electromagnetic fields. In a neutral atom qubit, they are hyperfin energy levels of an atom trapped in a focused laser beam. In a photonic qubit, they are different polarization states of a single photon. In a spin qubit in silicon, they are the spin-up and spin-down states of a single electron. The physical implementation varies, but the concept is the same. The qubit is prepared in a superposition, where it is simultaneously in both states, with a specific mathematical relationship between them, a relationship described by a complex number called the amplitude and a property called the phase. That phase relationship is the heart of everything. It is what allows quantum interference the ability to cancel out wrong answers and amplify right ones in a quantum algorithm. It is what allows entanglement, the quantum correlations between multiple qubits that give quantum computers their exponential power. The phase relationship between superposition states is the quantum information itself, and decoherence is the process by which the environment steals that phase relationship, scrambles it, and converts the quantum superposition into a classical mixture that carries no quantum information at all. Here is the physical mechanism that makes decoherence so inevitable and so devastating. Quantum mechanics tells us that the world at the smallest scales is described by wave functions, mathematical objects that contain complete information about a system state in the form of amplitudes and phases. When a qubit is in a superposition, its wave function describes both possibilities simultaneously. The quantum information the computation lives in the precise relationship between those possibilities. Now, the qubit does not exist in isolation. It is embedded in a physical system, a circuit, a crystal, a vacuum chamber, a laser trap, and that physical system is in constant contact with an environment. The environment contains thermal vibrations, electromagnetic fields fluctuating at every frequency, stray photons wandering in from outside, neighboring atoms and electrons jostling with their own quantum states every time the qubit interacts with any part of its environment, and the laws of quantum mechanics guarantee that any physical system interacts continuously with its environment. The environment becomes entangled with the qubit. From that point forward, the quantum state of the qubit cannot be described independently of the quantum state of the environment. The information about the qubit's phase is no longer contained only in the qubit. it has leaked irreversibly into the vast thermal reservoir of the environment. The qubit has not been measured by a detector, but the environment has effectively measured it in a thermodynamically irreversible way. The superposition collapses, the phase relationship is gone, the quantum information is destroyed, and this process, once it begins, is essentially irreversible, not because the laws of physics forbid reversal, but because reversing it would require tracking and controlling the quantum state of an astronomical number of environmental degrees of freedom simultaneously. And subscribe, because understanding why decoherence is irreversible is the key to understanding why defeating it requires such extraordinary engineering. The decoherence rate, how fast this destruction happens, is captured by two timescales that quantum hardware engineers care about obsessively. The first is T, called the energy relaxation time. This is how long it takes for a qubit that has been placed in its excited state to spontaneously decay back to its ground state by releasing energy into the environment. T sets an absolute ceiling on how long a qubit can be used. Once it has relaxed, the quantum information is gone. The second and more fundamental time scale is T, called the phase coherence time or dephasing time. This is how long the phase relationship, the precise mathematical relationship between the two superposition states, remains intact before environmental noise scrambles it. T is always less than or equal to twice T, and in practice is almost always significantly shorter. It is T that most directly limits how many quantum gate operations you can perform before errors accumulate beyond the threshold where error correction can fix them. In the superconducting qubits used by Google and IBM, T times are typically in the range of 100 to 500 microseconds for the best devices. T times are typically 50 to 300 microseconds. That sounds short, and it is. A quantum gate operation on a superconducting qubit takes roughly 10 to 100 nanoseconds. With a T of 100 microseconds, you can perform approximately 1,000 to 10,000 gate operations before decoherence destroys the computation. That is enough for small, shallow quantum circuits of the kind that have demonstrated quantum advantage on benchmarking tasks. It is nowhere near enough for the deep, complex circuits that useful fault-tolerant quantum algorithms require. Trapped I-don't qubits have much longer coherence times, t-values measured in seconds for the best systems, compared to microseconds for superconducting qubits, but trapped I-don't gate operations take microseconds rather than nanoseconds, so the actual number of gates you can perform before decoherence strikes is comparable in practice. Every qubit architecture faces the same fundamental adversary. The timescales are different. The physical mechanisms are different. The battle is the same. The sources of decoherence are as varied as the physical environments in which qubits must exist, and the engineers fighting decoherence must address all of them simultaneously, because even a single unaddressed decoherence channel can dominate the error rate and defeat all other protections. In superconducting qubits, the primary decoherence mechanisms include dielectric loss, dissipation of energy in the amorphous oxide layers that inevitably form on metal surfaces during fabrication, and quasi-particle tunneling, where thermally excited electrons in the superconducting material tunnel across the Josephson junction that defines the qubit and cause energy relaxation to level system defects, where atomic scale structural irregularities in the qubit's dielectric substrate create microscopic systems that can absorb and re-emit qubit energy, are a persistent source of decoherence that depends sensitively on the cleanliness of the fabrication process. Magnetic flux noise from fluctuating magnetic moments in surface oxides dephases flux-sensitive qubit designs. Even cosmic rays, high-energy particles from space, have been identified as a source of correlated qubit errors in superconducting systems, because a single cosmic ray event can deposit enough energy in a chip to cause simultaneous decoherence in many qubits through a process called phonon burst. The MIT Fermilab collaboration demonstrated in 2021 that cosmic ray events produce error bursts covering significant areas of a superconducting qubit chip, and that underground laboratory installation or shielding would be required to eliminate this decoherence channel in large-scale systems. For trapped I-don't qubits, the dominant decoherence mechanisms include laser frequency noise fluctuations in the laser beams used to perform gate operations, motional decoherence from the heating of the ions, vibrational modes in the electromagnetic trap, and photon scattering during laser operations. For spin qubits in silicon, the nuclear spin bath from surrounding silicon-29 atoms, about 4.7% of natural silicon atoms carry a nuclear spin, creates a fluctuating magnetic environment that dephases electron spins. The solution the field has adopted is isotopically purified silicon, enriched to more than 99.9% silicon-28, which carries no nuclear spin, creating a dramatically quieter magnetic environment. Quantum dots in isotopically purified silicon have achieved decoherence times of up to 10 milliseconds, among the longest ever measured for an electron spin in a solid. The materials science of decoherence suppression is itself a major field. Like and subscribe, because what Google, IBM, Microsoft, and the national laboratories are doing to fight decoherence in 2026 is where the story gets genuinely exciting. The quantum computing industry's primary response to decoherence is not to eliminate it. Eliminating decoherence entirely would require perfect isolation of the qubit from its environment, which violates the same physical requirements that allow the qubit to be controlled and measured. Instead, the response is quantum error correction, a mathematical framework for detecting and correcting the errors that decoherence creates fast enough and reliably enough to allow computation to proceed as if the qubits were perfect. The theoretical foundations of quantum error correction were laid by Peter Scheer and Andrew Steen in 1995 and 1996. The key insight is that you cannot copy a quantum state. The no-cloning theorem forbids it, but you can spread the quantum information across multiple physical qubits in an entangled logical qubit in a way that allows the errors on individual physical qubits to be detected and corrected without ever learning the value of the logical qubit. If the error rate on physical qubits is below a specific threshold value that depends on the error correction code, then adding more physical qubits to each logical qubit makes the logical qubit's error rate arbitrarily small. Error rates above the threshold mean adding more qubits makes things worse. Error rates below the threshold mean adding more qubits makes things better. This threshold theorem is the theoretical cornerstone of fault-tolerant quantum computing. For the surface code, the most widely studied error correction code for superconducting qubits, the threshold is approximately 1% error per gate. Google's Willow chip, announced in December 2024 and representing arguably the most significant quantum computing hardware milestone of the decade, was the first system to demonstrate below threshold error correction in practice by scaling from a 3 by 3 grid of encoded qubits to a 5 by 5 grid to a 7 by 7 grid. The Willow team showed that the logical error rate was cut in half each time the system scaled up. More qubits produced fewer errors. The threshold theorem works in the real world. This result, published in Nature, was the validation that the entire quantum error correction enterprise was waiting for. The barrier was not theoretical, it was engineering, and Willow proved the engineering was achievable. Peer-reviewed papers on quantum error correction tripled from 36 publications in all of 2024 to over 120 in the first 10 months of 2025 alone, reflecting the urgency with which the field responded to Willow's proof of concept. The challenge that remains, and it is still enormous, is the overhead of error correction. The surface code that Willow uses requires approximately 1,000 physical qubits to create one reliable logical qubit at the error rates current hardware achieves, and more aggressive estimates for useful fault-tolerant computation suggest that millions of physical qubits may be needed to run the algorithms that quantum computers are hoped to eventually solve. The distance between the 105-qubit Willow chip and a million-qubit fault-tolerant processor is not just a qubit count gap. It is an engineering civilization gap requiring advances in qubit fabrication, yield, control, electronics integration, cryogenic capacity, error correction, decoding speed, and system integration that each individually represent years of engineering work. IBM's roadmap targets fault-tolerant computation by 2029. Google has described a similar timeline. Amazon's partnership with Quera targets a fault-tolerant system on Amazon Break It by 2028. These timelines are credible based on the current trajectory of hardware improvement, but they are not guaranteed. The error correction overhead problem has motivated the search for codes with lower overhead. The KELD PC code's quantum low-density parity check codes theoretically require far fewer physical qubits per logical qubit than the surface code. Quantinum demonstrated real-time KELD PC decoding on their Helios-strapped I-don't processor using NVIDIA's NVLink quantum bridge. In early 2026, achieving 67 microsecond decoding latency 32 times faster than required. Quera demonstrated 96 logical qubits on their neutral atom system using KELD PC codes, showing that the theoretical overhead advantage is achievable in practice. These results, combined with Willow's below-threshold surface code demonstration, represent a coordinated advance across multiple platforms and multiple code families, the broadest simultaneous progress against decoherence through error correction that the field has ever seen. But error correction is not the only approach to managing decoherence, and the approaches that do not require vast qubit overhead are in some ways the most exciting developments of 2025 and 2026 because they attack the decoherence problem at its root rather than compensating for it after it occurs. Microsoft's Majorana 1 chip, unveiled in February 2025, takes the most radical approach. Instead of using conventional qubits and then correcting the errors that decoherence produces, topological qubits store quantum information in non-local quantum states called Majorana zero modes, exotic quantum particles whose defining property is that local noise cannot flip them because the quantum information is encoded in correlations between two spatially separated Majorana modes rather than in the local state of any single physical system. A perturbation at one location cannot access the quantum information because the information only exists in the relationship between two distant points. This topological protection is intrinsic, built into the physics of the qubit itself, not added on top through error correction overhead. Microsoft's published results in March 2025 in Nature demonstrated 8 topological qubits on a single chip fabricated using indium arsenide semiconductor combined with an aluminum superconducting layer with topological gap. Voltages around 120 microelectronvolts and a parity lifetime, the time before a topological bit flip measured in hours rather than microseconds. Microsoft describes this as hardware-protected qubits that are naturally resistant to the most common decoherence channels without requiring the massive physical qubit overhead of surface code error correction. The extraordinary claim parity lifetime measured in hours, if validated and reproducible at scale, would represent a transformation of the decoherence problem from the central engineering challenge of quantum computing to a solved problem at the physical hardware level before error correction even begins. The scientific community is still in the process of fully validating the Microsoft topological qubit results, and the path from 8 topological qubits to a fault-tolerant machine requires further demonstration of 2-qubit gate operations with high fidelity, but the directional claim that the physics of topological protection can dramatically reduce decoherence sensitivity is based on well-established quantum theory, and the March 2025 Nature paper provides the first experimental evidence that it can be realized in a manufacturable semiconductor device. Like and subscribe right now, because the next frontier in the decoherence fight takes the story somewhere nobody expected. The perovskite qubit results published at Linkping University in January 2026, with wide coverage from March 17, 2026, and the Cole Polytechnic superfluorescence result published in Nature in 2025, represent a third front in the fight against decoherence that is distinct from both error correction and topological protection. These materials results are attacking decoherence at the level of qubit host material selection, finding that certain crystal materials whose atomic interactions were assumed to be decoherence-inducing actually support quantum coherence through mechanisms that were not previously understood. The Linkping team demonstrated transition metal spin qubits in halide double perovskite crystals with T-coherence times of 29.5 microseconds at 4 Kelvin in a material that the entire field had written off as incompatible with quantum coherence because of its strong phonon coupling and dense nuclear spin bath, the coal. Polytechnic team observed room temperature superfluorescence in hybrid perovskites collective quantum coherent emission from many emitters simultaneously. At ambient temperatures in a solid state material, a 2025 research result extended quantum coherence in rare earth crystals 0.2 of milliseconds, boosting quantum communication range by a factor of 200. Together, these material discoveries point toward a future where the decoherence challenge is addressed not only through engineering at extreme temperatures, but through material design finding or creating crystals whose quantum physics naturally supports coherence rather than destroying it. The implications for scalability are significant. If qubits can be hosted in materials that are manufacturable through simple chemistry, tunable in their properties through composition changes, and operable at temperatures above millikelvin, the economic and engineering barriers that keep quantum computing confined to specialized facilities begin to dissolve. The dynamical decoupling techniques that quantum engineers deploy as a practical, near-term mitigation of decoherence deserve mention because they are already in use in real quantum systems today, including on the cloud-accessible quantum processors available through IBM Quantum, Amazon Braket, and IonQ. Dynamical decoupling works by applying carefully timed sequences of pulses to the qubit rotations of the quantum state that effectively average out the slowly varying magnetic and electric field fluctuations that cause dephasing. If the environment changes slowly compared to the timescale of the pulse sequence, the net effect of the environmental noise on the qubit's phase over a full pulse cycle is close to zero, extending the effective T-coherence time without requiring any additional qubits. Techniques like SPIM-Car-Purcell Myboomgil and XY8 dynamical decoupling sequences have been shown to extend T-coherence times by factors of 10 or more in specific hardware configurations. They do not eliminate decoherence. They buy time literally and figuratively, allowing quantum circuits to run for longer before errors accumulate beyond the correction threshold. In combination with error correction and improved hardware, dynamical decoupling forms the third pillar of the practical decoherence management toolkit that quantum engineers are deploying right now. The combination of all three approaches, error correction that tolerates the errors decoherence, creates topological protection that reduces intrinsic decoherence sensitivity, dynamical decoupling that extends coherence times in current hardware and new material discoveries that may change the physical platform entirely represents the most comprehensive and diverse attack on the decoherence problem in the history of quantum computing. The honest assessment of where this fight stands in the summer of 2026 is this: the quantum computing field has made more tangible, experimentally verified progress against decoherence in the past 18 months than in the decade that preceded it. Google's below-threshold error correction, Microsoft's topological qubit demonstration, Quantinum's real-time Keld PC decoding, Quera's 96 logical qubits, the perovskite material discoveries, the rare earth crystal coherence extension. These are not incremental improvements. They are qualitative demonstrations that the fundamental physics of error correction and coherence protection work in practice, not just in theory. And yet the gap between current systems and the fault-tolerant quantum computers that could run Shear's algorithm, simulate complex molecules, and solve commercially important optimization problems remains large. IBM's 2029 fault-tolerant timeline is credible. Amazon's 2028 Quera Libre deployment is credible. The U.S. Department of Energy's goal of a scientifically useful quantum computer by 2028 is credible. Credible does not mean guaranteed. The decoherence problem is not solved. It is being solved through a coordinated effort involving the world's best quantum hardware. Teams, the world's best theoretical physicists, and the world's most advanced fabrication facilities, spending billions of dollars and years of intellectual effort on a problem that is simultaneously one of the deepest in fundamental physics and one of the most practically consequential in modern technology. ICM's IPO prospectus was honest when it said that large-scale commercial traction may never occur. It would also be honest to say that the evidence from 2025 and 2026 makes the optimistic scenario. Quantum computing reaching fault-tolerant commercial utility within this decade more credible today than at any previous point in the field's history. Decoherence is the one quantum weakness that most people never hear explained. Now you have heard it explained. You know what it is, where it comes from, why it is so hard to fight, what every major approach to fighting it actually does at the physical level, and where the battle stands right now. If this video gave you that understanding, if decoherence is no longer just a word you have seen in headlines, but a physical phenomenon you genuinely understand, then please like this video and subscribe to this channel, because the quantum revolution is a story about physics, and the physics starts here.